Hi, my name is David Kale. I'm a professor in the Department of Statistical Science at Baylor University and the creator of the Baylorisms Project, a sneak peek of which I'm going to show you a bit of in this video. So in this video I'm going to give you an overview of the capabilities of the Univariate Probability Distributions tool and some of the things I found it really useful for. So here we go. We have it in front of us. You'll see that it's open in the Wolfram CDF player, which you'll need to download. It's a free tool. It's fairly large, but it's a very easy thing to get. All you have to do is give it your email address and affiliation if you have any. And once you've downloaded the actual CDF from the website where you're watching this video from, you'll be able to open the tool with no problem. And when you do, this is what you'll see. So you'll see this big panel right here in the middle, and you'll see a whole bunch of buttons and controls, which will probably look pretty overwhelming to begin with. So to start, you'll notice that the tool itself is kind of divided into two main parts. There's the kind of viewing panel up here, which right now just has a plot in it, and below you see all of the controls. Well, the controls themselves are divided into more or less three groups. They're the distribution buttons and controls. That's all of these guys here. And below that you see sim data. That's the actual simulated data, which is coming from the above distribution. And then the real data below, and this contains real data sets, which we'll talk about in just a moment. Additionally, there's this little options thing here, and if you click on the triangle right here, you see that there are a whole bunch of options which are available to you, and I'll talk about some of those as well. So to start with, let's just start with the kind of point of the module itself, which is to illustrate probability distributions, so the actual theoretical objects of statistics. And you can see these in various ways. So by default, what we're looking at here in the plotting window is the PDF, the probability density function, of the standard normal distribution, which is simply a bell curve. And if we like, we can just kind of hover over it and we see what the actual functional form of that is. So it's the exponential of a negative quadratic form there. And we see that the distribution has this nice bell shape, which is what we expect for the normal distribution. Additionally, if you've taken statistics classes, maybe you've heard of some other kinds of functions associated with the distribution. So we can get those as well. So I'll just unclick density to turn that off and click on hazard. So this is the hazard function of a probability distribution. I'll put the density here just so we can see these kind of in reference to one another. The CDF, which stands for the cumulative distribution function, so it's the integral of the density up until a point. The survival function, which is 1 minus the CDF. So those are functions related to the probability distribution, but there's also summary statistics, in a sense, of the distribution itself. So there's the mean of the distribution, also called the expected value, the median of that distribution, which in the normal distribution is the same. We can't actually see it here because it's actually 0, and it shows a little line, which is eclipsed by the y-axis, and box plot of the distribution. So the box plot here is actually designed, it's created in the exact same way as a usual box plot, meaning that we have our first quartile, our second or median quartile here, and the third quartile here, and then the 1.5 times the inner quartile range on the outside. But it's made for the actual distribution here. So those percentiles are actually computed off of the standard normal distribution in this case. Now, say we don't want the normal distribution. Let's suppose that we want a different distribution. Well, there are several distributions which are available to us. A lot of these are continuous distributions, so all the way from beta down here to uniform, these are all continuous distributions which we can select. And then below we have a whole bunch of discrete distributions as well, so Bernoulli, the beta binomial, all the way down to the Zipf distribution. The last one is multimodal, which is actually a mixture of normals, a mixture of Gaussians. So we can actually investigate that if we wanted to. And you see here we have two different two Gaussians which have been mixed to create one probability distribution. But let's not get ahead of ourselves. So going back to the normal distribution, we learn in statistics that distributions are parameterized by quantities which are useful for those distributions. So in this case, the normal distribution has parameters mean, which kind of governs where the actual distribution is, the location of the distribution. and its standard deviation, which is the square root of its variance, and that's governing how fat the distribution is. So how much variability there is in the distribution. If the standard deviation is small, then the distribution is very concentrated. If the standard deviation is large, then the distribution is very dispersed, and the samples that we get from that are also dispersed. Below, you'll notice here there's also this transform distribution spot. Remember, we're still kind of in the greater context of the distribution specifications and controls of the module. And you'll see that the transform distribution below. If you're familiar with location scale families, changing this 0 and 1 changes the location and scale of the family that we're looking at. So that will be useful later on when we talk about real data. For now, let's just keep going. The next place in the module that you'll see is the simulated data. This is one of the really nice parts of the module here. It allows us to actually simulate from this distribution. In other words, to take IID samples from the distribution that we're looking at of a given sample size. So to see that, I like to start with points. So if we click points here, we see that there are these green points down here, and those are representative of 50, so the sample size is below, 50 samples from the distribution that we've specified here. The normal distribution, which has a mean, well, we can see exactly what it is, a mean of 2 and a standard deviation of 0.72. So these green samples here are simply numbers which have been plotted. If we wanted to see the numbers, we can actually click print here, and the numbers actually show up. They've been rounded, but they show up up here. We can get rid of those if we like. And we can sample more if we'd like. So let's discard all of those and just keep sampling. We can sample over and over and over again. So we have a random number generator which is generating samples from this normal distribution. And you'll notice that they're all kind of clustered around the middle in general as we sample more and more. And that's just indicative of this kind of normal behavior. And one of the things that we learn in statistics is about the histogram. So if we have a collection of data and we'd like to, of continuous data, and we'd like to understand something about its distribution, one of the first things that we do is plot its histogram. So we simply bin up the number of data points. So we find the number of points which falls into each of these intervals, and then kind of make a little bar chart of the interval. And doing this, we can see what a histogram of normal data looks like, for example. And as you saw before, if I hover over, I can actually see the height here of the bar which has been drawn. Now this height, histograms can have various scales on the y-axis. You may be familiar with the count scale, also called the frequency scale, or the probability scale, which is the relative frequency scale. In this case, the histograms are all scaled according to their density, so that if I summed up the area of each of these rectangles, I would get 1. So it's a valid probability density function. And when we actually put it on that scale, we can actually compare the true probability density function, which is in the back there, the blue, and the histogram based on the data which was sampled from that probability distribution in the foreground. So we can compare them visually, and as we might expect, as the sample size increases to infinity, those two need to converge to one another. That would be an application of the law of large numbers. Now, if we go to smaller sample sizes, we can actually see what the variability will look like with smaller samples, even though they're from that distribution, which is a very useful thing to do. Similar to the histogram, in more sophisticated settings, you may see what's called a kernel density estimator, which is kind of a continuous version, in some sense, of a histogram, which is made not by making little boxes, but by standing little normal distributions on top of one another. So here is what the kernel density estimator would be for this same collection of data, so we can turn them on both at the same time if we'd like. Here is the, in green, the kernel density estimator of that based on that data. Now, you can actually see how this is working by decreasing the sample size to being fairly small, and using a little trick here. So I'll just kind of sample a bunch of times until I get a guy by himself, a sample by himself. So, for example, for this sample, you see that there's one dot here, and there's one kind of bell curve on top of it. And it turns out that that's exactly what the kernel density estimators are doing. They're just going to every single data point, say this one right here, and they're putting a little bell curve on top of it, and they're doing it for every single point, and then they add up the heights of those bell curves to get the green curve that you see here. Okay, so that's what a kernel density estimator is, and by clicking density under sim data down here, we're actually getting the density which has been estimated from the simulated data. So that's why the density for simulated data is different than the density for the distribution. The distribution is the actual true distribution, which is providing the samples. The simulated data is the density which has been estimated from those samples. And using that density, we can compute things like the hazard function or the CDF. These are all estimated. Sometimes you see these little strange bumps. You shouldn't worry about those. But all of the quantities which are viewed under sim data are in reference to the actual data itself. So when I click mean, this little triangle here is the sample mean of the data. So if I took all of the points which have been simulated, and I add them all up, and I divide by the number of points, which in this case is 50, then I would get the mean of the sample mean x bar, 2.1, which is distinct from the true mean of the distribution, which is right here, which is 2. Okay, and you can see how that varies just by resampling. Okay. Similarly, of course, you can see the median and also the box plot of the data. So this is something which is useful because we see it in elementary courses where we want to make a box plot of data. Well, we can actually see this happening. So here I have a box plot, and I'll go ahead and erase the points. And you can see how the box plot changes just based on different samples, all from the same distribution. Okay, we can put the points on top. We can do all sorts of things. We can compare them to the actual box plot of the true distribution, and so on. Okay, so that's a useful thing to do with the module when we're trying to understand things like box plots. Now, one of the things that we've learned in statistics education is that students actually understand certain concepts a lot better when they see them in reference to real data sets. So this module also contains a number of real data sets which the student may find helpful to understand certain concepts. So to start, let's look at this Old Faithful data set. This is a pretty famous data set in statistics. I'll go ahead and turn off the distribution density, and when I change to Old Faithful, it looks like nothing has been done. You'll notice that on the original scale, the scales themselves have changed. But let's go ahead and just plot the points of that. You'll see that there's kind of these two clusters, and we'll plot a histogram. So this is the histogram of the Old Faithful data set. And by looking at this, we're probably already willing to believe that this thing is bimodal. Okay, the actual distribution that these samples are coming from is bimodal. If we wanted to, we could plot a density, which is a kernel density estimator based on this real data, not the simulated data now. And one of the things that we may want to do is we may want to try to fit a distribution to this data. Well, what distribution should we start with? Obviously, there's no kind of normal distribution which kind of matches that histogram. But this actually illustrates the problem which is helped out by the transform distribution. Since the scales of this normal distribution are fixed, we kind of can't get it over far enough as we like to match all of the real data sets. So what we've done here is we've gone ahead and allowed the user to transform the location and scale of the underlying distribution, and you can manually set it, or you can just click auto, and it will actually try to compute one for you. So here's a good location and good scale. If we are using a normal distribution, which we've already said is really not a good idea, well, since it is a bimodal distribution, what would be a good idea? It turns out that the only distribution that we have here which really exhibits good bimodal behavior is the multimodal distribution, which is simply a mixture of normal distributions. So here we have that. I'm going to go ahead and reset the location scale, which resets the location scale to 0 and 1, and I'll go ahead and refit that again just to give me a good approximation of what a good location scale may be for this particular data set. It takes a moment because actually it's running an algorithm behind the scenes to actually try to find a good location and scale. And here we go. The location is 4.3 and the scale is 1.1. Okay, so that's kind of giving us a baseline of this bimodal distribution. Now, we can change where the mode is of each of the distributions individually by simply going and changing this, the mu1. This is the mean of that first distribution. Remember, this is a mixture of two distributions. So here I'm just moving mu1, and it looks like maybe it's a little thinner. This isn't going to fit perfectly because, as you can tell, it looks like this this part of the distribution of real data is bimodal. So it is bimodal, but it's skewed in this part and in this part. This part is skewed this way, this part is skewed that way. So we can't really match that behavior perfectly with two normal distributions, a mixture of two normals, but we can get kind of close. So let's see how we can do. The one on the left seems to be centered in the right place, and maybe the dispersion looks about right. The one on the right side, maybe its mean needs to be a little bit larger, but it actually looks pretty good as it is. The problem is, in this case, is that the mixture weights are actually identical, which we want to change probably if we're going to do this particular problem. So in this case, we're seeing more samples from this right distribution as opposed to the left. So to actually translate that into the blue distributions, the theoretical distributions that we're looking at, we could do it one of two ways. We could take the weight of the probability of the first one down, or we could take the weight of the second one up. I'm going to do that. Okay, so as we do that, notice that the left is going down, the right is going up. So we're getting closer here. This looks something that's more or less reasonable. Maybe the mean should be a little less here. So the point being that the parameters themselves, mu and sigma, are on an absolute scale, but the parameters pi, the actual weights for the mixture, are on a relative scale. This is the only difference for this particular distribution. And the goal of a statistician in most cases is to try to kind of find a distribution which replicates the data that you see. Well, this distribution looks decent from the actual histogram, comparing that to the mixture of two normals. Let's see if the actual points which are simulated from the normals mimic those simulated from, or mimic those points which come from the real data set. So as we increase our sample sizes, we're seeing that the points are more or less similar. Maybe I need to tailor. I'm looking at this right here, and I see that the green line is maybe a little offset to the right of the red one. The red one, remember, is just the actual data points themselves, and looks like the green data set may be a little bit too variable, so I can kind of decrease this a little bit. Not so much. There we go. And now I have something which looks a little bit more reasonable in terms of the actual data which is simulated. The data simulated from the distribution which I've created here actually matches the data which was observed pretty well. So if I compare these, I can, I guess, put on two histograms now, not just one. And I can see what happens as I resample, so it's not just one sample. And it looks like it does fairly decent, not perfect, but we can see that the Old Faithful data set is a bimodal data set, which can be fit relatively well by a mixture of two normal distributions. So this is just one of the examples where real data can help. There are other examples, such as the TIPS data set, which, let's go ahead and get rid of these things which were here. So now I'm looking at the totally wrong distribution. I'll go back to the normal. Now let's look at the histogram of tips. So the tips data set was just, some waiter was collecting tips and just writing down what those tips were for each of their bills. So using the tips data set, we can illustrate things like skewness. So in this data set, we see a heavy positive skewness. So if we were trying to fit it, maybe we would try to fit this with a chi-square distribution or a gamma distribution or something like that. And we could just go to gamma. We could show the actual density here. Now, if you're familiar with gamma distributions, this is going to look kind of strange because the gamma distribution, usually we think of it starting at 0, but the location and the scale have still been set as before. So we need to go ahead and reset those. So now it's going back to 0 and 1, and we can change the parameters of the gamma distribution, our alpha and beta. We can change them accordingly to find a distribution which seems to fit or seems to match what the data is doing fairly well. So you can play around with this yourself and figure out what you think is best for this particular case. The overarching point here is that for real data sets, what we like to do is we like to try to find distributions, theoretical distributions, which mimic those real data sets very well. And that process is called fitting. So if you've been in a statistics class and you've computed an x bar and an s, for example, that's how we would, in many cases, find the mean and the standard deviation of a normal distribution if we were trying to fit a normal distribution. There are different formulas which one would use for alpha and beta if we were looking at the gamma distribution. But since this module is interactive, we can actually just kind of play with those parameters until everything kind of looks right. So that's the basic idea. Now, let's go ahead and get rid of the real data and kind of go back to the initial settings. So to do that, we can just click this little plus sign up here, go to initial settings. That's going to reset the module for us so that everything is a totally fresh session, just like it was when we opened it up for the first time. And what I'd like to do now is just show you some of the other things which are useful with the module. So I'll begin by going to the binomial distribution. You'll notice that this is a binomial 1 pi distribution, and pi is set to 1/2, so this is a coin flip. And we can do things like see a whole bunch of coin flips. So in this case, we would be looking at 31, let's go to something around 30 coin flips. And we can see what actually the probability of seeing 15 heads is, 16 heads is, 17, and so on. And we'll notice that there's this bell kind of shape coming in that would be indicative of that normal approximation to the binomial as a consequence of the central limit theorem. So we can illustrate concepts like that very easily. Similarly, we can simulate points. Notice that the points here stack on top of one another. That's because in 50 samples, so what is the actual experiment here? The experiment is flipping a coin 30 times and counting up the number of heads, and we've done that experiment 50 times. So there's actually 50 green dots here. But each one is somewhat transparent, so some look darker than the others because they're stacked on top of one another. That effect is called overplotting, and the transparency helps a little bit, but even better, jittering helps quite a bit more. Okay, so the jittering, it's just randomly adding a little bit of noise so the points aren't all on top of one another, and the amount of noise is just enough so that the points will never kind of cross over and stack on one another. Okay, we should always be able to see especially with kind of smaller ends. As things get bunched up too much, you can't. But the module itself is trying to be smart and not allow these things to overlap one another, so you can see really which dot is coming from which point. Okay, so for example, all of these right here, all of these green dots were 11s. So there were 11 heads out of, in this case, 22 samples. So let's go back to our 30. Okay. Now, we can make histograms just like before, but histograms in this case aren't terribly useful. You wouldn't actually do this in practice. You would probably make little bar charts. Well, to do that, that's just changing the histogram bin setting to a smaller bin. So we change our bin setting to smaller bins. This would be effectively a bar chart for the number of times that you see each of those outcomes. So, for example, the height here is actually a density scaled version of the number of heads that we saw out of the number of times we saw 15 heads. Sorry, out of 30 flips, and in doing that experiment 200 times. So all of these things are available. Histogram bin width is a topic which comes up, is a very important topic at the beginning of many elementary applied statistics courses. So you can illustrate that with going to options, histogram and density options, the histogram for the simulated data, and then just changing the bin number. You'll notice also that there are some binning methods which are standard in statistics, Scott's rule, Sturgis rule, and so on, each of which, if you click them, it will actually implement the number of bins according to that rule. Otherwise, there are a number of things that you may want to just change in terms of the actual plot itself. One of them is the axes. So if you go to axes options, you can turn off the y-axis if you'd like, and you can even turn off the x-axis if you would like, which makes for kind of interesting looking plots. Or you can change actually the window that we're looking at. So for example, say that we want to illustrate things, now it's complaining at me. Say that we want to illustrate a very large x scale. So x is 100. And so we don't want the x scale to actually change with the number of trials. Now, I'll go ahead and turn off the points here. I'll turn off the histogram. And you can see kind of what's going on. As the number of trials increases, you see that bell-shaped curve behavior kind of come in stronger and stronger. And while we're at it, so I'll go back to the automatic scaling here and turn both of my axes back on. One thing which is useful is to see when the normal approximation to the binomial breaks down. So theory says that kind of if for any fixed pi, as long as it's not 0 or 1 and n goes to infinity, then we have this bell curve approximation will work. But if n is fixed, then you can kind of see places where the normal approximation will get bad, right? Which is kind of when pi is close to 1 or pi is close to 0, that's when we advise don't use the normal approximation because bad things can happen. Whereas if pi is kind of more moderate towards 50%, then the bell curve approximation, the normal approximation to the binomial, is a fairly decent one. There are also general options, which you can see. Print options, so that's going to govern actually the size of so here we can actually have individual coin flips. We can change the size of that font by simply going to the font size down here. Notice that it's getting larger up top, and the window is getting very large, so have to kind of be careful here. General plot options. This is useful for projectors. Sometimes projectors make everything look a lot bigger, so we can change that by changing the plot size, so small or large. Random number generation. If you're familiar with things like random number generator seeds and so on, you can actually manually set those. Those would allow your students to replicate exactly what you're doing, even though they're using random numbers as well. It's because the random numbers are generated according to the same process. One last thing that you'll probably find helpful, which is under options, is color and style options. That is actually allowing you to change things like the color of these dots. You'll notice that everything in distribution, meaning all of these functions and so on, they all have that same blue color. Okay, and that's to help the user understand visually that all of the things that are blue, those are the actual theoretical distributions themselves. Everything coming from green, those are actually from the simulated data. Okay, so it's taking the simulated data and it's creating a kernel density estimator. The real data is coming in a reddish color. Now, it could be that those aren't the colors that you'd like. You'd like something else. So to change those, you can simply, I'll go ahead here and turn off the simulated things. Go to color and style options, and I'll show you how to do this for distribution. For density, size is referring to the thickness of that line. So we can actually kind of just take that down altogether. Dashing, if we like it to be kind of dashed, there's the dashing going on in there now. And fill opacity, which is actually showing you, well, how dark, like how opaque should that be? Should it be just totally clear, so there's no color at all? Or should it be totally opaque and you can't see through it? In some cases that's useful, in some cases it's not. To change the color, we can simply click on the color scheme down here, and if I wanted to make it yellow, this is how I would do it. And now the inside is yellow. If I went to the hazard function isn't changed with it. So I would need to change the hazard function, the CDF survival or box plot in turn to actually get the same things there. And you can do this for every one of them. So not just the distribution density, but the simulated data density and the data density and so on. So I'll go ahead here and reset all of the settings, as things have become kind of strange here, and leave it at that. So that's the univariate probability distributions module. And if you have questions, let me know. My email address can be found at the Baylor Department of Statistical Science webpage. Thanks.